Imagine the scenario. It is the summer holidays and you are traveling from your city to your hometown to visit your grandparents. As you look out the window, all you see are these huge transmission lines and transformers all over the countryside. And you wonder to yourself, why do these devices, why do these transformers and these overhead wires have to use such high voltages, 11 kilovolts, 30 kilovolts, even 100 kilovolts? Why can't they use some lower voltage which is comparatively less dangerous? To understand why, we have to understand electrical energy and the concept of potential difference and what happens to electrons or charges inside a conductor. So first of all, what is electrical energy? It is the energy produced from electrical potential energy or kinetic energy of charged particles. It can be defined as the energy generated by the movement of electrons. For example, let us consider this system where we have two spheres A and B which are charged to different amounts. So sphere A has more charge compared to sphere B. Or we can say that sphere A has positive charge while sphere B has excess negative charge. If you were to connect these two spheres with a conducting wire, there would be a flow of charge. We would say that sphere A is at a higher potential and sphere B is at a lower potential. So in moving the charges from this to this sphere, there is a change in the potential which we call potential difference, which is equal to VA minus VB. That is the potential of sphere A minus the potential of sphere B. What happens to the electrons as they are moving through that conductor? That will tell us the answer to the next question, that why are transformers installed? Let us investigate this a little further. In this system, you see a voltage source like a battery connected to a conductor. So the potential at point A is greater than the potential at point B. So conventional current will be flowing from point A to point B. Since the current is flowing from A to B, the electrical potential at A is higher compared to B. So VA is greater than VB. And that means that the difference between VA and VB, that is VA minus VB, will be greater than 0. It will be positive. So the charge is flowing across a positive potential difference. Now, what is the change in the potential energy between the points A and B? So the change in potential energy delta U pot is equal to the final potential energy minus the initial potential energy. So that is equal to delta Q bracket VB minus VA. Now remember that VB is less than VA, which means that this subtraction will have a negative result. So delta U potential is equal to negative delta Q times V. Now if you remember, Q is equal to I multiplied by T. So if you substitute Q in the previous equation, we get a new relationship, that is delta U potential is equal to negative I times V times delta T, which is less than 0. Now you can ask the question, what is this energy converting into? Well, in this system, the electrical potential energy of the system is converting into the kinetic energy of the charge carriers. So delta K is the kinetic energy of the charge carriers, and that energy is coming from the transformation of the potential energy, which means an increase in delta K is equal to a decrease in potential energy, which is why we have a negative sign on this side. Now, delta K can also be written as I times V times delta T by substituting from the previous equation. And that tells us what is going on inside the conductor. The electrical potential difference in this conductor is converted into the kinetic energy of the charge carriers as they are moving from high potential to low potential. Unfortunately, this conversion is not perfect, and it is not perfect because the charges are constantly in collisions with the positive ions and other imperfections inside the conductor. And during each of these collisions, energy is being liberated in the form of waste heat. So we see that charge carriers do not move with constant acceleration, but at a steady drift velocity because of the constant collisions with the ions and atoms during their transit. Now, the amount of energy dissipated as heat in the conductor during a time interval delta T can be given as delta W, that is the dissipated energy, is equal to I times V times delta T. The power of a system is the energy dissipated per unit time. So we can write this mathematically as P is equal to delta W divided by delta T. And the unit of power is obviously watt. So since P is equal to delta W by delta T, and we know that P is equal to I multiplied by V, and from Ohm's law, We also know that V is equal to I times R. We can perform a substitution that gives us P is equal to I square R, or P is equal to V square upon R. Now, these equations are of critical importance in understanding why we require those transformers and why we require those very, very high voltages. Since P is equal to I square R or V square by R, it is this power which is heating up, for example, the coil of an electrical bulb to incandescence, causing it to release light and heat. So what you are seeing here is the release of the potential energy that was stored in the system in the form of heat energy and light energy. The same process even happens in other systems. For example, if you look at a battery or a galvanic cell, you will notice that as you use up the cell, it heats up. That is because the electrical potential that is coming from the chemical energy stored in the battery is also converted into waste heat during the operation of the battery. So heat is produced in the bulb connected across the terminals of a cell, and the energy is distributed in the bulb as well, coming from the chemical energy of the electrolyte. So both the bulb and the cell are heating up due to the waste heat generated in this process. And that tells us why we require those overhead cables at high voltages in power transmission. Because the question here is how to reduce the power loss. The power is dissipated in the connecting wires and is wasted in the form of PC. We can write this as PC is equal to I square RC, or PC is equal to P square RC divided by V square, where P is the supplied power to the system. You will notice here that the power wasted during transmission is inversely proportional to the square of voltage. That means the higher the transmission voltage, the less power will be dissipated as waste heat in the system. And that is why we require transformers. The purpose of transformers is to step up the voltage to very high levels so that we can reduce the amount of power lost during transmission. Now let's summarize what we have learned so far.
Manorama Horizon. Learning made simple.